So what we're going to study today is observers, okay? Here is why observers are so important. Let me share my screen. You have this information in the presentation. However, I highly recommend you that you follow this in here. And ask me a lot of questions because this is pretty much the last class, okay? So observers, okay? We have a plant. Imagine there is a black box, okay? And from this black box, we have only the output of the system. And of course, we know the input to the system, okay? But we are interested into using x1, x2, up to xn, okay? Which are the internal variables. How can we measure them if this is a closed box? We're not able to open it. We're not able sometimes to measure it. So if we have these kind of systems that are quite difficult to obtain a model in state space, and that is also quite difficult to measure directly the internal variables, then what we do is we make an observer to make an estimation on the internal variables, okay? So what we do is from this system, okay, the system that has a model, we know that the model of the system is the derivative of x is a times x plus b times u, where the output is equal to c times x, okay? So what we're going to do is we're going to create another set of variables, another dynamical system, but one that we can have all the information from it, okay? This is quite relevant, okay? So what we are going to do is we're going to create another model that is going to be with a new set of variables that are x bar, okay? Or they can be O, okay? It's any other variable that we want, okay? I will call them O for simplicity, okay? From the observers, okay? And these are going to be the observed variables, okay? I think in the presentation they are x bar or x with a hat, something like that. Don't worry about it. I mean, it's just only a different set of variables, okay? Then what we're going to do is we're going to make a copy of the model. So let's say that the variable O, the derivative of the variable O, is equal to A times O plus B times U plus something else, okay? Where the output of the system, of this system, not this one, not the original one, but the observed system, I will call it S, is equal to C times O, okay? So basically, you see what I'm doing is I'm creating another system with another set of variables, but this one, I will make it from scratch. I know everything about it, okay? And this one, I can access the internal variables, okay? So we're going to do an example on that. So what I'm going to add in here is something that is called a gain times what do we know about this system? What do we really know about this one? And here we can measure the output. Okay, let's use the output. Y minus the observed output. Okay? So this is what is going to be called an observer. Okay? Now, when can we create an observer? Similarly to when we can create a state feedback that places the pole anywhere we want. For that, we require the system to be controllable. Okay? For us to make an observer, we will require the system to be observable. Okay? And that property is going to be reviewed like this. The observability matrix is equal to C times A, C times A squared, and so on until C times A up to n minus 1. Okay. This is going to be the observability matrix. Okay. If and only if the rank of the observability matrix is equal to n, it implies that the system is observable. Okay. So first we need the system to be observable. Okay. And if the system has this property, then we're going to create this mathematical entity that we call observer. Okay. And this mathematical entity is implemented, could be implemented in a microcontroller, could be implemented in a real system with op-amps, could be implemented in many ways. Okay. This you don't have to do in the final physical project, but you'll have to learn how to make simulations on this. Okay. So but we have, you see, two different systems. We have one with a variable called X and another one with a variable called O. Okay. So when will this work? When will this actually follow, or this estimation of the variable X is going to be good? When that is good and when it's not. Okay. So what we're going to do is I'm going to propose an error system, okay, an observation error system, okay? Okay. In this observation error, let me call it E, where this is going to be X minus O, okay? Then what I'm going to do is I'm going to do the derivative of this one. Okay. What is X dot? X dot is AX plus BU. Okay. Minus, what is O dot? AO plus BU. Sorry. Plus L that multiplies the output minus the observed output. Okay? Is this correct? It comes from the definition that I have up here. Okay, this is X dot and this is O dot. Okay? So now let's put everything that corresponds together. This is going to be A times X minus O plus B times U minus B times U minus L times Y minus S. But do we know what Y is? Y is? And what is S? We do know what it is. Okay? So I'm going to write, instead of Y, I'm going to write C times X. And instead of S, I'm going to write C times O. Okay? So this is equal to A times X minus O plus, you see, B and B, this gets canceled. Okay? So then, actually what I'll have here is a minus. Minus L times C times X minus C times O. Okay? So I can make a factorization, you see. This is going to be equal to A times X minus O minus L times C times X minus O. And I can even factorize this. A minus LC times X minus O. But you see, what is X minus O? Is this observed error. Okay? So this observer that I'm proposing, I mean, this one is actually called a Luenberger observer. Okay? Because of the researcher who solved this, who proposed this observer. His name is Luenberger. Okay? So we understand this equation. It's a matrix times something. This is the derivative. So when is this stable and when is this unstable? Okay, so if the poles, I mean the eigenvalues of A minus LC have real part negative, then this system is stable, right? Then the error is going to be equal to its derivative, and it's going to be equal to 0. And if this is equal to 0, X minus O is going to be equal to 0, which means that X can be approximated by O. Okay? So we're creating a mathematical entity that can estimate the state of a system. Okay? So let's do an example and hope that this gets a bit clarified. Okay? Let's start with making A equal to 0, 2, 3, 1, 5, 2, minus 2, 3, 1. Okay, this is matrix A. Let's make matrix B equal to 0, 1, 2, transposed. And let's say that matrix C is equal to 1, 0, 0, meaning X1 is the output of the system. Okay? Let's see what happens in here. Okay? The controllability matrix, first of all, is it controllable? The rank of the controllability matrix is equal to 3. Therefore, this system is controllable. Okay? Now, let's see what about the observability matrix. The observability matrix, we said it's C. And on the second row, C times A. And on the third row is C times A squared. Okay? Or we can write obs V and A and C. Okay? This is how we can compute it automatically in MATLAB. And the rank of the observability matrix is 3. So the system is observable. So we can control it and we can observe its internal variables. Okay, we can estimate the internal variables of the system. Okay. So just so this is clear, I will make a system just executing this command. So sys is actually a variable that contains this system, and G is going to be the transfer function of this one. Okay? So here is a transfer function. As you can see, there are sign changes. Therefore, the system is unstable. Okay? Of course, the roots of 1, -6, 3, and -29 are the same as the eigenvalues of matrix A. Okay, as we should expect. Good? So far, so good? Yeah. We have just checked what is the observability matrix. We have seen that this is observable. We have just checked the controllability matrix. We have seen that this is controllable. And we have now two different representations, okay? A state space system representation and a transfer function representation. Nothing more than that, okay? Now, let me go to Simulink. Let me bring the library scope. Now, I'm going to use this control system toolbox. And inside of here, I'm going to put G, okay, which is the transfer function representation of this system. Okay? Let's just wait for this to wake up. So we know that this system is unstable. We want to make it stable. We know that we can make it stable because the system is controllable. So we can place the poles anywhere we want. Okay? So this is G. Okay? Do we know how to make the state space feedback, the state feedback? We do. You remember that it was minus K times X plus UV, right? I will put in here minus K. I haven't designed it yet, but this is minus K. Okay? This is the output of the system. Okay? Where do I have X in here? What are the state variables? They are inside of here somewhere, but I cannot access them. Okay? That is the problem. That's why I need to build an observer. Okay? Because I don't have a way to measure X from here. Okay? I need to make an estimation of it. Okay? So, since I don't have that, what I'm going to do, I'm going to make an observer. And I know what the observer is. Okay? The observer is this equation that I have in here. So, I will say that this is matrix A. And this here is O. Okay? Now, the derivative of O is equal to A times O plus B times U. Okay, then I need B. But I will also need L. Again, I haven't designed it, but I will in a moment, okay? Need 3 additions. What I have in here is the derivative of O, right? What do I need to do in order to obtain O? I need to make the integral of it. I will integrate it. I'll put an initial condition. Okay? And this is O. Okay? What is going to be multiplied by L? You see? You need Y and you need S. Y, we have it in here. So that's not a problem. Okay, so this is Y. So we'll connect Y in here. And where do I have S, which was the output of the observed system? I have it in here. If this is the O, this is O, right? So A times O is what I call S, right? I'm going to put this in here. And this one will be multiplied in here times L. Okay, so this is the equation that I'm writing. A times O plus B times U, so this is the input, plus L times the output of the system minus the output of the observer, okay? Is this clear so far? I'm just implementing the equations that we just did, okay? Now, this is not necessary, but I will write this just because I want this to be a point of reference. So I want a comparison point, okay? So I'm going to have in here dx I will put it in here. Yeah, there is a question here. I haven't solved the matrix K or L or any of those. I haven't solved them, okay? I'm going to do it in a moment, Alan, okay? What I proposed, what I know now is A, B, oh, sorry, this is C, okay? So what I'm going to do in here is just a copy of the system, the real one. So A times X plus B times U, and then in here I will have the derivative of X, and if I multiply this one times C, what I will have out here is the output of the system, okay? Sorry, I'm missing the integral. I need to put here the integral. Good. And then I need to connect this one. Oh, sorry. Here. Okay. So this is the system in its state space representation. Okay. This one is just going to be for comparison purposes. Okay, so all that I'm going to use is what comes from the transfer function where I don't have X. Okay, but I will have it in here just as a comparison point. Okay, I will put in here initial conditions equal to 0, and I will plot, just so you believe me that it is exactly the same. I will plot the output from the system in the state space representation together with the output of the real of the system in transfer function. Okay. So in order to make both of them exactly the same, I will put the exact same input to both. A unit step. Yeah, of course, there are some errors. Let me quickly design the value of K and the value of L. Okay, so this is how we're going to design K. We saw this last class. K is equal to acre of A, B, and where do you want the poles of the system in closed loop? Let's say that we want them in -1, -2, and -3. Okay, so this is the gain that will make that the poles of the system in closed loop are -1, -2, and -3. Okay. And L, for now, I'm going to make L equal to 0. Okay. So I'm not going to use the observer at all. I just want to compare the output of the system and the in transfer function representation and the output of the system in state space representation. Okay. Let me see what are the errors. Sorry. There are several errors. This is a quite common error. We have to change them matrix K times U. It's good if you do it in the first one and then you copy it and then it's okay, but I didn't do it, so I have to change all of them. Okay, sorry for that. But still, it's a common error and one that I am sure that you will face, so don't worry about that, just fix it. Matrix K times U. I think now it should work. You see, the output of the system is exactly the same. Okay? The same at any time. Okay? So both the state space representation and the transfer function contain the same information. Okay? So as I just mentioned, this is only for comparison purposes. So I don't need it. Okay? That's why I'm just going to pull it down here. So I'm going to work with this part, okay, which is the observer. I have said that for the observer to work, the poles of A minus L times C should be negative as well. Okay? So we have a way to solve this in MATLAB. Okay? So L is going to be equal to acre. And in here, what we're going to write is A transposed. This is important, okay? A transposed, C transposed, and then we're going to write in here what are the poles that we want in closed loop, okay? The poles of the observer for the system to work in closed loop have to be faster than the poles of the system in closed loop. Okay, so in that sense, the fastest pole that I used in here is -3. I'm going to write in here -10, -11, minus 12, okay, which is faster. Okay. Oh, I'm sorry, this should be a column. That's why I'm going to do the transposed, because I want this to be a column. In this sense, the poles of matrix A minus L times C are going to be minus 10, minus 11, and minus 12. So the error, the observation error, is going to be a stable system. Okay? So let's go back here. So what I'm going to do is the input to the observer has to be the exact same input as the system. You remember in the equation? In here, oh, sorry. In here we said that the input in both systems are the same. Okay? So it has to be exactly the same. So what I'm going to do now is this, that is the output of the observed system. I'm also going to add it in here. I'm going to put 3 inputs now. For now, I'm going to put the exact same initial condition, 0. And this one, I will connect it to S. Okay. Again, I make the simulation. And then you see that all of them have the same dynamics. Okay. They look like the same. Okay. It's not that cool because they all have the same initial condition, but we're going to make a difference now. Okay. So for now, let's assume that the observer is working. Okay. So what I'm going to do, since we believe that the observer is working, what I'm going to do is, what is the closest that we have to X in order to make the state feedback? We don't have X. Well, we have it down here, but we're not going to use it because this is just for comparison purposes, we said. But in here, where do I have X? I don't have X, but I have something that looks like X. What is that? What is the closest that I have to X? Any idea of what can I use in here? O, exactly. O is the closest that I have. So what I'm going to use is O to make the input to the system. Okay. So what I'm going to do is I will also put it like this. So the input is going to be minus K times O, which is the closest that I have instead of X. And then I will connect this here. You remember that we put a gain last time? I put a gain equal to 1 now. Okay. So this is going to be the input here, and this is going to be the input to the observer as well. Okay, so this is the system, this is the observer. Both of them have the exact same input. Okay, just to make this exactly equal, I will also put it in here in my comparison system. Okay, so all the systems have the exact same input. I'm going to simulate again. Oops. Again, the same mistake, you see? Matrix K times U. Again, let's hit play. Now, you see? Now everything is 0. The system is no longer unstable. Okay? But what would happen if I change the initial conditions of the observer? I will just put 1, 0, and -1 as the initial conditions. We have 3 state variables. That's why I'm writing 3 initial conditions. Then here, oops, this became unstable. Let me see what happened. Let me go back here. Check where is the problem. So the cow is invested with UV. Let me check. This shouldn't be a problem. This shouldn't be a problem. I will put it here 0. Yeah, it's still unstable. Let me check why. There must be an error in here of the ABC. This initial condition is no problem, but we said that it was 1, 0, and -1. Let me just check. The O is AO plus B times U plus L times Y. Yeah, that's correct. Then in here, minus K times X. This goes in here, this goes in here. They all have the same. Let me just double check. This one is stable. This one is also stable. A minus LC. It's the output. Okay, let's change this. I'm just going to change the solver to avoid any issue, but I don't think that's going to be the issue, but still. I'm going to use a fixed step, and I'm going to use an Euler extrapolation. Okay. Oh, let me change the step. I want it to be very, very small. Okay. Yeah, this is B. See, perfect. Hey. Let me just check which one is the one that is unstable. You see, this one is still, no. You see, the unstable one is the one below, so it doesn't really matter. I will fix that now. But you see, what you have in here is now the system has a transient state where it is a bit different because they both have different initial conditions, but then they all look the same, both of them. So the output of the observer, which is this one, is exactly the same as the output of the real system. Okay? Now, let me just check why this one below here is unstable, because this shouldn't. This is A, this is B times U. Let me see why this one becomes unstable so fast. You see, this one is becoming unstable in here. We actually lose it from here. But why is this going unstable? Is it the same input? Yeah, it's the same input. Probably. No, there shouldn't be a problem, but still. That's the same. I don't get what this is becoming unstable. Yeah. I don't get why this one is becoming unstable, but this is the one that is unstable. But anyway, let's just focus now on this. As you see, we have been able to make stable the output of this system that has only input and output. And the one in here with the observer, let me just move this a little bit so we have clear what the observer is. Okay. So everything that we have in here is the observer. Okay. Then the output of the observer, which is the state variables, the estimation of the state variables, we multiply by minus k times u. And then we put it in here. Now, what happens if I put a gain in here equal to 1? As we expect, the output now is going to be different from 1. Okay? You see, we have this steady state value. Okay, it's close to minus 2.5. Actually, yeah, minus 2.5. So what I can do is I'm going to put in here 1 divided by minus 2.5. Oh, sorry, minus 2.5. So now the output should go to 1. Okay. And this is the observer working. You see, it has a different initial condition than the original system, but still it follows it. Okay. And it works. Okay. It's making a good estimation of the state variables. Okay. Now, just to make this work, just as a reference, what I will do is I'm going to connect this one in here. I'm going to connect in here instead of this one. I will use the output of the one below. Let's see if this fixes the situation. Oh, it doesn't. Let me just, I'll disconnect this one from here and see if these other two, they are the same. Yeah, apparently I cannot use both at the same time. See, I don't know why. I'll put this equal to 0. But you see, I have the exact same behavior with the other one. Okay. Unfortunately, I cannot use both in parallel at the same time. Okay. But still, as you see, I'm not using X anywhere. Okay. I'm just using the output of this system. You see, X is not used at all. But what I'm going to do is, let's quickly make a comparison. What would happen if I compare X1 and X1? Let me use, in signal routing, we have something that is called a demux. Okay, so the demux, we have 3 state variables. Let's use in here to connect this to X and another one that we will connect to O. Then let's compare X1 with O1. You see? First, it has a transient, and then they're exactly the same. I will do the same with X2 and O2. You see? The transient is different, but after a transient state, it goes and follows it exactly. So this is the estimation of the state variables. Okay? And if we do the same with X3, we connect this one to O and we connect this one to X. You see, again, a transient, and after a while, the X are exactly the same. Okay? So, as you can see, we can use an observer to estimate the state variables. Okay? So this is what an observer is. Okay? The observer does an estimation of the real state variables, and then what we do is we can control a system with that. Okay? Any doubt about here, about this? Is this clear? How do we define the values of matrix A, B, and C? That comes from modeling, Abraham. Okay? That comes from our model. So either we have that as an input, we know the model of the system, A, B, and C, or from a transfer function, we obtain a state space representation. Okay? So if you have a transfer function, for instance, let me quickly do that. If you have this transfer function, let's say that this is your model, you can obtain a state space representation of this one. You see, this would be matrix A, this would be matrix B, and this would be matrix C. That is a possible state space representation. It's different than the one that I used in this example, but as we mentioned before, we have an infinite amount of state space representation per transfer function. Okay. Good.
Teacher?
Yes.
Can you hear me?
Yeah, now I can hear you. I don't know why.
Okay, nice. This is going to help us with the fourth project, the fourth simulation project?
Yes. The first one project, you have to make an observer.
Okay.
Okay. So the mandatory topics are state feedback and observer for the simulation project.
And both of those topics are going to be in the final exam?
Yes, both of them are going to be in the final exam. Okay.
Okay. For when is the fourth simulation project?
1 day before the exam, that is the due date.
29?
Yeah.
Okay, thank you.
29th. And as I mentioned before, if you don't want to do the final simulation project, send me an email and say that you agree that those points are graded with your final exam. Okay? But the final exam is going to be pretty much similar to the simulation project. So if you know how to do that, you will not have any problems in the final exam. So my recommendation is, if you don't make the report, make sure that you know how to do a state feedback and an observer for a third order system. Okay? Good. So